Chapter 3, Reactance and Impedance, Resistance, Inductance, and Capacitive Circuits, RLC circuits. If we were to plot the current and voltage on a time graph for a very simple AC circuit consisting of an AC voltage source, ET, and a resistor, R, it would look something like this. The blue is the voltage across the resistor, which, because it's connected directly to the source, is also the ET source voltage, and the red dotted line is the current in the circuit as well as the resistor. This is sometimes referred to as the time domain. Because the resistor simply and directly resists the flow of electrons at all periods of time, the waveform for the voltage drop across the resistor, ER, is exactly in phase with the waveform for the current through it, IR, which in this series circuit, and because there is only one passive element, R, in the circuit, is equal to the circuit current I. And the voltage drop, as I have said, across the resistor ER is equal to the source voltage ET. We can look at any point in time along the horizontal axis of the plot and compare those values of current and voltage with each other. Any snapshot look at the values of the waves are referred to as instantaneous values, meaning the values at that instant in time. The resistor of any given size will impede AC current as defined by Ohm's law and is proportional to the voltage across it divided by the current through it. And when defining using phasor notation, it is sometimes referred to as the reactance of the resistor and designated as X subscript R. XR, of course, is in phase with IR, as well as the voltage drop across it, ER. In this case, of only one passive element, and it is directly connected across the source voltage, ER will equal ET, the source voltage. We can also calculate the power dissipated by the resistor by multiplying the instantaneous voltage times the instantaneous current, or P will equal V times I, and plot those values on the same graph. Note that the power is never negative in value. When the current is positive above the line, the voltage is also positive, resulting in a positive value. Conversely, when the current is negative below the line, the voltage is also negative, which means the result is positive and it will yield a positive value for power. A negative number, remember, multiplied by a negative number equals a positive number. This consistent polarity of power tells us that the resistor is always dissipating power, taking it from the source and releasing it in the form of heat energy. Whether the current is positive or negative, a resistor still dissipates energy. This time, we're going to insert a second element in this series circuit, and that passive element is going to be an inductor. Because it's still a series circuit, the current through each of the elements, the resistor and the inductor, I in the series circuit is going to be the same current in the inductor as in the resistor. I'm going to designate the voltage drop across the inductor as EL, and I'm going to designate the current through the inductor as IL. And we are going to concentrate on only the voltage and current with regard to the inductor. So the time graph, the time domain graph of this current and voltage will look like this. Remember, the voltage drop across an inductor is a reaction against the change in current through it. Therefore, the instantaneous voltage is zero whenever the instantaneous current is at a peak. That is where there is relatively zero change going on, or a level slope on the current sine wave. And the instantaneous voltage is at a peak whenever the instantaneous current is at a maximum change, the points of steepest slope on the current wave, and that is where it crosses the zero line. This results in a voltage wave that is 90 degrees out of phase with the current wave. Looking at the graph, the voltage wave seems to have a head start on the current. The voltage leads the current, or the current lags behind the voltage. The phasors would look like this. The voltage leads the current by 90 degrees, or you might say the current lags the voltage by 90 degrees. When dealing with AC voltage applied to an inductor, it's always confusing to try and remember if the current leads the voltage or the current lags the voltage. The way I do remember it, is going back to our DC circuit when we apply DC to the inductor with a switch, which is similar to starting the first half cycle of an AC wave. When we start at applying a positive value of voltage to the inductor, the current will start at zero and start to rise slowly to a maximum value as it builds the magnetic field. However, as soon as the switch is closed, the voltage is immediately applied to the inductor. So the voltage is immediate. It goes right to the maximum value, whereas the current takes a while to build up the magnetic field. So the current would lag the voltage. An inductor's opposition to change in current translates to an opposition to alternating current in general, which is, by definition, sinusoidal and always changing in instantaneous magnitude and direction. This opposition to alternating current is similar to resistance, but different in that it is always resulting in a 90-degree phase shift between the current and the voltage. Because of the differences, it has a different name: reactance. Reactance to AC is expressed in ohms, just as resistance is, except that it is indicated with a mathematical symbol X with a subscript L. X instead of R. To be specific, reactance associated with an inductor is usually symbolized by a capital letter X with a letter L as a subscript following it, like this. We have already seen the relationship between voltage drop across an inductor and the current through it. That is, the voltage will lead the current by 90 degrees. The inductor of a given size will impede AC current similar to the resistance of a resistor. That resistance is defined by Ohm's law to be proportional to the voltage across it divided by the current through it. In phasor terms, it is defined by the voltage phasor divided by the current phasor, and is in phase with the current. The reactance of an inductor is also defined by Ohm's law to be proportional to the voltage across it divided by the current through it. But in phasor terms, we define it by this equation, which includes both magnitude and direction. It is calculated to be 90 degrees leading the current. The phasor is sometimes written with a J operator as J times XL, and XL is a phasor itself. Since inductors drop voltage in proportion to the rate of current change, they will drop more voltage for faster changing currents and less voltage for slower changing currents. What this means is that the magnitude of the reactance in ohms for any inductor is directly proportional to the frequency of the alternating current. Also, the magnitude of the reactance is directly proportional to the inductance of the inductor. The exact formula for determining reactance is the magnitude of XL is equal to 2 pi FL, where F is the frequency in hertz or cycles per second, pi is just 3.14159, etc., and L is the inductance in henries. Let's consider a series RL circuit with a supply voltage of ET. The resistor will offer resistance to AC current, while the inductor will offer resistance in the form of reactance to the AC current. This combined opposition will be a combination of resistance and reactance. In order to express the opposition succinctly, we need a more comprehensive term for opposition to current other than resistance or reactance alone. This term is called impedance. Its symbol is Z, and in this case we're going to put a subscript T after it because it's the total impedance of the circuit. And it's expressed in units of ohms, just like resistance. If we take a closer look at this series resistor inductor circuit, we know that the current through each element of a series circuit is the same because that's the characteristic of a series circuit. The current in each element of the circuit is equal to I. In other words, the current through the resistor is equal to the current through the inductor is equal to the current of the supply current. And those currents are vectors or phasors. We just learned from the previous slides that the voltage drop across the resistor is in phase with the current in the circuit, and that the voltage drop across the inductor is 90 degrees out of phase with the current. In other words, the inductor voltage leads the current by 90 degrees, giving us this orientation of phasors of the current and voltage in the circuit. We know from Kirchhoff's voltage law that the voltage drops around the circuit has to add up to 0 degrees. In other words, the voltage drop across the resistor and the inductor have to equal the voltage of the source. And in this case, this is what the vectors would look like, where the phasor ER, when added to the phasor EL, must equal the phasor ET of the source. You can see from the phasor diagram that the current is at 0 degrees. In other words, we're using the current as our reference phasor, in which case the voltage across the resistor will be in phase with that current. and it's shown in the diagram as such. And the voltage across the inductor will be 90 degrees to the voltage across the resistor. We can rewrite our Kirchhoff's voltage law equation using polar notation. This time, I will rewrite the angles of the phasors, which means that the phasor ET, the source voltage, will be the sum of the phasors ER plus EL, which is ER at 0 degrees plus EL at 90 degrees, giving us the result of ET at phi degrees, as I've indicated in the diagram. I'm going to move that equation down here for the moment, and I'm going to divide each element of the equation by the current now. I can do that as long as I divide both sides of the equation by the same thing, which I'm doing. So I divide the ET at phi degrees by I at 0 degrees, and I divide the voltage ER at 0 degrees with the current I at 0 degrees, and I've divided EL at 90 degrees by the current at 0 degrees. Now, if you look at the equation, you could see that the resistance voltage ER at 0 degrees all over I at 0 degrees is nothing more than the reactance of the resistor, or it's just the resistor in this case, because that's Ohm's law. Voltage over current will equal the resistance. I've indicated it as a reactance, but it is also the resistance, but represented by X subscript R. And the last component of that equation, EL at 90 degrees all over I at 0 degrees, is the reactance of the inductor. We already saw that a couple of slides back, and if we add those two together, we get ZT, which is the total impedance of the circuit. As long as we add up the phasors, it will result in the components ZT, which is also equal to ET at phi degrees all over I at 0 degrees, which is equal to the magnitude ZT at phi degrees, which is the angle of ZT with XR, which is the same angle as the angle between ET and the current in the circuit. Now let's cement some of this theory by looking at an example. Let's put some real numbers in this circuit and see how it works. We're still dealing in North American frequencies, so we're still looking at a 60 hertz system. We have the resistor equaling 5 ohms, and we're having the inductor equal 10 millihenries. We know that the reactance of the inductor will be given by 2 pi FL, and we know that the 10 millihenries is 10 over 1,000 henries, so that will give us 2 times 3.14159 times 60 cycles a second times 10 over 100 henries, which when you calculate that out would come to 3.7699 ohms. So if we want to know what the total impedance is, we have to add the resistance and the inductance together, which are phasors. So we have to use phasor terms, which is 5 ohms at 0 degrees for the resistor and 3.7699 ohms at 90 degrees for the inductor reactance. Or we can express that in rectangular coordinate form, giving us both forms if we want, and we can plot those impedance vectors or phasors, as you see here. Now, if the voltage in this circuit were, say, 100 volts, we could say, let's let the 100 volts be our reference phasor, which is going to be at 0 degrees if it's a reference. And I've drawn the phasor here in blue. And we just have to use Ohm's law to calculate the circuit current, which is ET all over ZT, remembering that, of course, that ET and ZT are phasors themselves, which would be 100 at 0 degrees volts all over 6.262 at 37.016 degrees, and that would be an impedance in ohms. And if you divide the numerator by the denominator, you're going to get exactly 160 milliamps at minus 37 degrees, which when plotted next to the voltage would look like this. I'm going to replace the inductor with a capacitor this time. It's going to be the same series circuit, a resistor in series with a capacitor this time, source voltage being ET, and the current through the circuit is going to be designated I. The voltage drop across the capacitor is going to be designated E subscript C, and the current through the capacitor is going to be I subscript C. But because it's a series circuit and there's only 2 passive elements in the circuit, then the total current in the circuit is going to equal the same current through the resistor as through the capacitor. Having said all of that, the time domain curves would look like this, where the current through the capacitor and the circuit is shown as a dotted red line, and the voltage across the capacitor is shown as a blue solid line. Remember, the current through the capacitor is a reaction against the change in voltage across it. Therefore, the instantaneous current is 0 whenever the instantaneous voltage is at a peak. 0 change or a level slope on the voltage sine wave. And the instantaneous current is at a peak whenever the instantaneous voltage is at a maximum change, the points of the steepest slopes on the voltage wave, where it crosses. This results in a voltage wave that is 90 degrees out of phase with the current wave. Looking at the graph, the current wave seems to have a head start on the voltage wave. The current leads the voltage, or the voltage lags behind the current. The phasors would look like this. The capacitor voltage lags the circuit current by 90 degrees, or you might say the current leads the capacitor voltage by 90 degrees. I have also shown the voltage drop across the resistor, which is in phase with the current, of course. As with an inductor, the capacitor also presents a kind of a memory problem here, where you trying to remember whether the current will lag or lead the voltage across either the inductor or the capacitor. We know that there's a 90-degree phase shift, but as time goes on, sometimes it's hard to remember. At least for me, it was hard to remember which is which, unless you go back like I have with the inductor, and instead of considering an AC circuit, let's consider a DC circuit. And this time we are going to put a battery in series with the capacitor, and the battery is going to switch on DC voltage to the capacitor as soon as the switch is closed, of course. And this is going to simulate the rise of the positive half cycle of an AC circuit. But it's easier to think of it in terms of DC. So what happens when you close the switch on a DC circuit? You close the switch and the voltage across the capacitor is 0 to start with, and it starts to rise because the capacitor will start to charge up. And the more it charges up, the more it will resist the current flow. The current will then start to decrease till the capacitor is fully charged, of course, and then there is no current flowing and there's no charge building up anymore. The charge is already there and it is exactly equal to the supply voltage. So what you've seen here is that the current will be instantaneous when you close the switch. So it'll be at the full value, only limited by the current through the resistor, which is limited by Ohm's law. Bottom line here is you're going to have instantaneous current flowing, and the voltage drop across the capacitor is going to be 0 and slowly building up. So the current will lead the voltage in this case. And if you think of it as the positive half cycle of an AC circuit, the voltage is going to be lagging the current as well. So if the voltage is lagging the current in the positive half cycle, then it's going to be lagging for all of the cycles. So this is a way of remembering whether the voltage is leading or lagging in the case of a capacitive circuit. The current flow in a capacitor. The current flow in a capacitor is related to the change in the voltage of the capacitor, which is sinusoidal and always changing in magnitude, and defines the opposition to alternating current in general. The opposition to alternating current is similar to resistance, but different in that it is always resulting in a 90-degree phase shift between the current and the voltage. Because of this difference, it has a different name: reactance. As with inductors, the reactance of a capacitor is expressed in ohms and symbolized by the letter X, or XC to be more specific when referencing a capacitor in this case. We have already seen the relationship between the voltage drop across a capacitor and the current through it. That is, the voltage will lag the current by 90 degrees. A capacitor of a given size will impede AC current similar to the resistance of a resistor. That resistance is defined by Ohm's law to be proportional to the voltage across it divided by the current through it. In phasor terms, it is defined by the resistor voltage phasor divided by the current phasor through the resistor. The reactance of a capacitor is also defined by Ohm's law to be proportional to the voltage across it divided by the current through it. But in phasors terms, it is the magnitude of the capacitor voltage at minus 90 degrees to the current, which is at 0 degrees with reference to the voltage across it. Well, XC is just EC all over IC, which is XC at minus 90 degrees. The phasor is sometimes written with a J operator as a minus J in front of the XC. Since capacitors conduct current in proportion to the rate of change of the voltage, they will pass more current for faster changing voltages and less current for slower changing voltages. What this means is that reactance in ohms for any capacitor is inversely proportional to the frequency of the alternating current, and notably also inversely proportional to the capacitance of the capacitor. The actual formula being Xc is equal to 1 divided by 2 pi Fc, where F is the frequency in hertz or cycles per second, pi is 3.14159, and C is the capacitance in farads. Let's have a closer look at this series RC circuit. The resistor will offer resistive reactance to the AC current, while the capacitor will offer resistance in the form of capacitive reactance to the AC current. Because the resistor's reactance is in phase with the current, the capacitor's reactance is at minus 90 degrees. The combined effect of the two components will be an opposition to the current equal to the sum of the two numbers. In other words, it's a phasor sum. And that phasor sum, if the component is made up of capacitive reactance and resistance, then it is referred to as impedance. And it is given the letter Z, and sometimes it has a subscript denoting that it's the total reactance in the system. However, Z is often referred to as the impedance of the circuit. Because this is a series circuit with current in all of the elements of this circuit, the currents are equal. And we have just learned that the voltage drop across a resistor in a circuit is in phase with the current, and the voltage drop across the capacitor is 90 degrees lagging. And the impedance of the circuit is made up of the vector or phasor sum of the impedance of the resistor and the capacitor. Kirchhoff's voltage law also tells us that the sum of the voltages in the series circuit have to add to zero. Therefore, the sum of the voltage drops on the resistor and the voltage drop on the capacitor is equal to the source voltage, which is ET. I'm going to rewrite the equation in polar notation. And I'm going to let the current be our reference phasor. In other words, the current I'm setting at 0 degrees, and all other phasors will be referenced to our current phasor. So the voltage equation written in polar notation is ET at phi degrees. Now phi will be the sum of the voltage drop across the resistor and the voltage drop across the capacitor, and we'll set ET at phi degrees, and it is equal to ER at 0 degrees plus EC at minus 90 degrees. Moving the equation to give me a little bit more room to manipulate here, I am now going to divide each of those voltage elements of the equation by the same thing, the phasor I at 0 degrees, or the circuit current. So we have a new formula here, which is ET at phi degrees over the phasor I at 0 degrees equal to ER over the current and EC over the same current. Now, if you look at the equation, you will see that the resistance voltage ER at 0 degrees all over the current is nothing more than the reactance of the resistor, or it's just the resistance of the resistor, because That's Ohm's law. Voltage over the current will equal the resistance. I've indicated that the reactance here, that it's a reactance here, but it's really a resistance. But we represented it by X subscript R. And the last component of the equation, EC at minus 90 degrees all over the current, is the reactance of the capacitor. If we add those two together, we get ZT, which is the total impedance of the circuit, as long as we add up the phasors. Now, ZT, which is equal to ET at phi degrees all over the current, can be described as our impedance, ZT, at phi degrees, because ET at phi degrees divided by I at 0 degrees gives us ZT at phi degrees, which is the angle between the impedance ZT and XR, the reactance of the resistor. It is also exactly equal to the angle between the supply voltage and the current. One thing you will notice is that the angle phi, the contained angle of ZT with the horizontal, is the same angle as ET with the current, which is not surprising because the triangle formed by XR, XC, and ZT is proportional to the triangle formed by ER, EC, and ET, because in the voltage phasor equation, it is divided by the same thing, the current, I at 0 degrees. So the angles should all be the same. It's just the magnitudes that are different. So the triangles formed by XR, XC, and ZT is definitely proportional to the voltage triangle. So let's do a quick example here. We have an RC circuit, a series circuit here in series with an AC supply voltage. We're going to let the resistor in this circuit equal 5 ohms. And we're going to let the capacitor equal 100 microfarads. And we're going to calculate the total impedance of the circuit. And we're going to use the standard system frequency for North America, which is 60 hertz. We know that reactance for a capacitor is given by 1 over 2 pi Fc. So in numbers, that would be 1 all over the quantity 2 times 3.14159 times 60 times 100 over 1,000, which is 100 over 1,000 microfarads. And if you multiply all of that out, you will get the reactance of the capacitor is 26.5258 ohms. The total impedance for the circuit is the 5 ohm resistor plus the 26.5258 ohm capacitive reactance. But those are phasors, which are 5 at 0 degrees plus 26.5258 at minus 90 degrees. Or in rectangular form, it's 5 plus J0 plus 0 minus J 26.5258, which is easier to add than the polar form. And that would give us 5 at minus J 26.5258, or 26.993 at minus 79.325 degrees. Now, if we do a quick review of what we've learned, if we're looking at just a resistor in an AC circuit, we describe the reactance of the resistor as just the resistance itself, and the phasor is X subscript R at 0 degrees, or in phasor notation just X subscript R. And because it's just a passive resistor element, the current and the voltage are going to be in phase with the reactance. So everything is easy to work out, everything is in phase, and you can see it in our phasor diagram here. The next thing we added to the circuit was an inductor, and now we have a alternating current source in series with a resistor, in series with an inductor. We've already looked at the reactance of the resistor. The reactance of the inductor, the magnitude, is given by 2 pi FL, where F is the frequency and L is the inductance in henries. If we're to write that in the form of a polar notation or a phasor, it would be the magnitude at plus 90 degrees. And in rectangular format, it would be J times X subscript L. And the phasor diagram for the impedance is shown at the bottom of the diagram there. The total impedance ZT is made up of the sum of the reactance of the resistor and the reactance of the inductor. If we added the source voltage, we would find that it's in phase with the total impedance of the circuit, which is not unusual. It would lie along the same direction as the impedance ZT, but the current for the circuit is going to be displaced by phi degrees, which is a product of the, or actually it's the result of adding the reactance of the resistor and the reactance of the inductor together, and it gives us the same phase angle as the phase angle between ZT and XR, and that is the phase angle for the impedance as well as the voltage and current of this series circuit. We then replaced the inductor with a capacitor, and we found that the magnitude of the capacitance was 1 over 2 pi FC, and in phasor notation, it would be XC at minus 90 degrees, or in rectangular notation, it would be minus JXC. And the two impedances, one for the two reactances, one for the resistor and one for the capacitor, add up, as you see there in the phasors, to give us the total impedance of the circuit, ZT. And if we drew in the voltage vector for the circuit, the total circuit, and the current in the circuit, it would have the same angle as the angle of the ZT with XR, and we went through that process as well, but we would find that the voltage in this case is lagging the current by phi degrees. Now, if we were going to use Ohm's law using our phasors and reactances and impedances, it would be the same as we would be using for the DC circuit, but this time instead of resistance, we have impedance. And the voltage is still going to be equal to the current times the impedance. But in this case, you have to remember we are using phasors, not absolute values. So it's E is equal to IZ, or I is equal to E over Z, or Z is equal to E over I. It's the same equation for Ohm's law for a DC circuit, only this time we're using AC quantities and we're using reactances and impedances. What you do have to remember is that all quantities are phasors, and they have to be used with the rules regarding vector analysis. Let's work out another more complex example. It's still a series circuit, but this time we have a 120 volt, 60 hertz AC supply feeding a resistor, inductor, and a capacitor. The impedance of the resistor is given as 250 ohms. The inductance is given as 650 millihenries, and the capacitance is given as 1.5 microfarads. Well, we have to get all of the components reading in terms of impedances. So we're going to convert or figure out what the impedance of the inductor is. It's just 2 pi FL, which is 2 times pi times 60 times 650 all over 1,000, which works out to 245.04 ohms. And to calculate the impedance of the capacitor, we have to change the capacitance into an impedance, and that's 1 over 2 pi FC. The 2 pi 60 hertz is the same. The 1.5 microfarads is just 1.5 all over a million, which it works out to 1.7684 K. And the impedance of the resistor is already given in ohms. It's 250 plus J0 ohms in rectangular format, and 250 ohms at 0 degrees in polar format. So we have all of the impedances now in terms of reactances or impedances. And they're all listed right there. What we can do now is fill out a table for the voltage, current, and impedance of all the components in the circuit. So we have all the components listed across the top of the table, and all of the values that we're looking for listed along the left-hand side, or the rows of the table. And we're going to figure out everything in volts, amps, and ohms. So we'll start with the voltage supply, which is easy. We don't have to do any calculations there. It's 120 volts at 60 hertz, which means it's 120 plus J0 in rectangular format, and it's 120 at 0 degrees in polar format. The impedances we have already calculated, and we've got them marked on the diagram above the table there, but I've listed them in both polar notation as well as rectangular notation, and we can use them back and forth during our calculations depending on when we're adding, subtracting, multiplying, or dividing. So the total impedance for the circuit, because it's in series, is just ZR plus ZL plus ZC, which we are going to use the rectangular notation to start off with, because that's the easiest one to add. And if you add that all up, you'll get 250 at minus J 1.5233 k ohms. And you can convert that to polar form notation as well, which is 1.5437 k ohms at minus 80.680 degrees. And we can put that in our table at the bottom right-hand corner, which is the total impedance for the circuit. And we're going to use that total impedance now to calculate the total current for the circuit, and we're going to use Ohm's law, which means it's just the total voltage over the total impedance of the circuit. But we have to remember that we are using phasor notation, so it's going to be the 120 volts all over the total impedance for the circuit. And to do that calculation, because it is a division of two phasors, we're going to use the polar notation, which is the voltage 120 at 0 degrees divided by 1.5437 k ohms at minus 80.68 degrees, which will result in 77.734 milliamps, that's what the M is for, at plus 80.68 degrees. And we know that it's a series circuit, so the current through each element is the same. So we can fill in those boxes just by repeating what is the total current for the circuit. And then the calculation for the voltage drop across each component in the circuit is, again, just using Ohm's law. In this time, E is equal to I times Z. And again, it's phasor notation. But because we're doing a multiplication, this time we're going to still use the polar notation. So if we fill in those boxes, we will get the voltage drop on the resistor is 19.434 at 80.680 degrees. For the inductor, it's 19.048 at 170.68 degrees. And for the capacitance, it's 137.46 at minus 9.3199. And you might have noticed something if you were observant, and that is the fact that the voltage across the capacitor is in excess of any other voltage in the circuit, including the source voltage. So what is happening here is you're getting a resonant frequency, or a ringing of resonant frequency in the system, which will actually happen as you approach the resonant frequency of the system, and it will push voltages in excess of the source voltage. But we will leave that for now, because this is the end of the chapter.